Hey guys, let's look at another example or an application of our control volume problems. This one's going to be for turbines. Everybody has seen a turbine if you've ever been on an airplane, commercial airplane, that is. If you look in the engines, you'll see it has all those little blades and the blades will spin around. All right, that's a turbine. Now, a turbine, what it does is it develops power as a result of a gas or liquid that's passing through a set of blades. All right, so the blades are going to rotate, and essentially that rotation is going to help us develop power. Now, in this application, we're going to be ignoring kinetic and potential energy effects. So if you were to look at your energy balance equation, we would have 0 equals QCV dot minus WCV dot plus m dot times h1 minus h2. All right, so we're going to assume steady state here. So that's how we get the 0 on the left side. But a turbine is just going to be another application of this problem. And if you want to know more about how a turbine works, you can Google that. There are lots of videos online explaining how it works. But that's basically what it is. The air will rotate those blades. That rotation can then be used to generate power. Okay, so let's go into an example for this one. We've got steam at a pressure of 1800 psi. Temperature is 1100 degrees Fahrenheit. It's entering a turbine that is operating at steady state. 20% of this mass flow is extracted at a pressure of 600 psi and a temperature of 500 degrees Fahrenheit. The rest of that steam is going to exit as saturated vapor at a pressure of 1 psi. The turbine is going to develop a power output of 6.8 times 10 to the 6th BTU per hour, and heat transfer from the turbine to the surroundings occurs at the rate of 5 times 10 to the 4th BTU per hour. We will neglect kinetic and potential effects. We want to find the mass flow rate of the steam as it enters the turbine in pounds per second. And then here is our picture. So essentially we've got flow coming in here. It's going to rotate the blades, which then causes this shaft to rotate. Okay. And then if you have some other device attached to this rotating shaft, you could, operate a machine, something like that. Okay. So let's look for keywords. First, we've got steady state. Always want to pay attention to that. It tells us that at the exit, we have saturated vapor. Want to pay attention to that. Here we've got a power output of 6.8 times 10 to the 6th. And then we have heat transfer from the turbine to the surroundings is occurring at this rate. So those are going to be our main terms to pay attention to in that problem statement. Now let's go ahead and get started. So on this one, we're going to neglect kinetic and potential energy effects. So let's just go ahead and write down this equation, because that's going to be the equation we will use, because again, this is steady state. This equation here was for steady state. Actually, let's write that down. So this one is assuming steady state conditions. Okay, so our equation will be that 0 equals QCV dot minus WCV dot plus m dot times h1 minus h2. Now, in this case, we've got 2 exits, right? So this is only for one inlet, one exit, so we need to write this for multiple inlets and outlets. Here I called it inputs here instead. The equation that we will have for multiple inlets and outlets will be 0 equals Q dot minus the W dot plus the summation over all the inlets of Mi dot Hi minus the sum over all the outlets of m dot out times h out. Now, that's what we'll use for this problem, okay? We originally started with that, which that's a fine equation. If you only have one inlet, one outlet, we need to expand it, though, to make it work for two outlets. Now that we've got that established, let's go ahead and write out our equation using our 1, 2, and 3 notation. We're still going to have 0 on the left. We'll have that equal to Q dot minus W dot plus M1 dot times H1. That's for the inlet. Now the outlets you're going to subtract. So we're going to have minus M2 dot times H2 and minus M3 dot times H3. Now notice we have M1 dot, M2 dot, M3 dot. Our problem wants us to find M1 dot. That's what this is asking for here. So this is what we are looking for. Now we still have to have M2 dot and M3 dot. We were told that 20% of M1 dot will give us M2 dot. So at least we have an equation for that. We don't yet have one for M3 dot. So think about how we could figure that out. We needed another equation here. Now remember, we've got steady state going on, so that gives us another equation for mass flow. Basically what's coming in has to equal what's going out. So that means M1 dot has to equal M2 dot plus M3 dot. So this gives us another equation, so that's a good thing. Let's go ahead and write down the fact that M2 dot is 20% of M1 dot, so we know that equation also. And if the rest of the flow comes out at exit 3 here, that means, I shouldn't be putting arrows here, those don't lead to each other. Let's put an and. That means M3 dot is equal to 80% of M1 dot. Now we've got these three equations that we can use. Notice we have these two in terms of M1 dot. So that's good. We've reduced the number of variables that we have. So let's replace these, put them in this equation up here. So we'll have 0 equals Q dot minus W dot plus M1 dot times H1 minus 0.2 times H2 and then minus 0.8 times H3. All we did here was pull out the M1 dot from these terms. Okay. Now what we're looking for is this right here. Okay. So let's go ahead and solve this equation for M1 dot. M1 dot is going to be W dot minus Q dot over H1 minus the 0.2 H2 minus the 0.8 H3. We have numbers for these two things up here at the top. Let's plug those in, and then after that we will worry about the H's. W dot. We need to know about a power output. So these W dots are typically going to be a power input, power output, something like that. We have a power output of 6.8 times 10 to the 6th. Now you have to figure out the sign. Is this positive or negative? We know the value, but what's the sign? Let's write the value down. Now if we're generating a power output, I always think about it as we have excess power, we're sending it out. It's going to be positive. We have an excess, so it's going to be positive. Okay. The Q dot, for this one, we've got heat transfer from the turbine to the surroundings. So we're sending energy due to heat out of the system. That is going to be a negative value. So we'll have minus a negative 5 times 10 to the 4th BTU per hour for Q dot. Now these are in hour. We don't want M dot to be in units of hours. because it wants pounds per second. Let's convert this using the conversion of 1 hour per 3,600 seconds. And now we need to divide by our H1 minus 0.2 H2 minus 0.8 H3. Almost done. We got to look at these three enthalpy values. These are going to require the tables, of course. Let's look at H1 first. So let's put H1. Now pay attention to the pressure we're at. We are at a pressure of 1800 psi. And the temperature there is 1100 degrees Fahrenheit. Now with this, we're going to have to go to the table, if you don't know already what this is, because you have to figure out, do you have superheated vapor, what do you have here? It already says it's steam, so that should kind of clue you in, but just to be thorough, let's look at this so you can see how we determine that. Our pressure is 1800 psi. If you go to the saturated water table, the saturation temperature is 621.21 degrees Fahrenheit. Our temperature is 1100. This is way larger than that saturation temperature, so this is superheated vapor. That means we need table A4E. If you go to that table, look up this combination. Whoops, paper's falling. What you will get for H1 is 1,542.5. That's BTU per pound. Now for the second exit right here, exit 2, for this one, our pressure, it's lower. It's now at 600 psi, and our temperature is a lot lower. That's 500 degrees Fahrenheit. Again, we're going to have to figure out what we have here. Okay, so we're going to go to saturated water table. You're going to find your pressure of 600, which is here. Look at the saturation temperature. It's 486.33. Compare it to this. Our number is still higher than that. That means we still have superheated vapor. And let's just put, just to have the note, we'll put because T2 is greater than the saturation temperature. That way you don't forget the logic we used there. So for this, we need to go to table A4E again, and then find H2. Guys, my paper keeps falling. Let me use this one. There we go. Now, our H2 value that we're going to have, if you look up these conditions, you will have 1,216.2. That's going to be BTU per pound. Now let's do the same thing for H3. For H3, we've just got a pressure given to us, but we are told we have saturated vapor. And the pressure was 1 psi. If we've got saturated vapor, that's telling you to use the saturated water table. So let's use, I've been calling it the liquid vapor table, so that's the one we will use. That's table A3. And then for this one, at this pressure, pressure of 1 psi, our H value, if we look over here, come over here to H, we need Hg because we have saturated vapor. So that's at that G point on the vapor dome. We have 1105.8. That'll be the H value we need. 1105.8, and that's BTU per pound. Now what you would do is you would take these three values. I'm out of room here, so I'm not going to write it out. But take those three values, and then you're just going to plug them into this equation. Let's call this equation 1. And then you will find your mass flow. So let's put plug H1, H2, and H3 into equation 1. Your mass flow that you get then at the inlet is going to be 4.589 pounds per second. Okay. So that's how you go through a problem like that. Again, we keep going back to these tables. So in these problems for these applications, you're always going to use that energy balance equation. Main thing you need to do is pay attention to if you have steady state or not. If you have steady state, you get to use the simplified equation where the left side is equal to 0, and you can use that simple mass flow in equals mass flow out. All right, hopefully y'all found that helpful. I will see you guys next time.